Well, in this module, we're going to be looking at a couple of major concepts, and there are many components to them. And one is ventilation. And so in this first part of the module, we're going to look at just all aspects of ventilation. And then the second part of the module, we're going to look at oxygenation and just how we look at those concepts, and of course, how we apply those concepts. So you'll note in this slide here, we have a couple of graphics that actually look at, give me a second here. That actually look at, trying to get my laser pointer, what is an EGAN in your assigned readings. And I want to take a look at two of the graphics from there and then apply it to a graphic representation of the lungs and airways. So if you go to the beginning of ventilation module and readings, you'll see that there's a graphic that just takes the lung as really one unit, and we'll take a look at this and deconstruct it so you can really take a look at it. And then in terms of a table 11.1, which is an EGAN, we're looking at some concepts that we look at in terms of respiratory system mechanics. And so we want to have some kind of baseline place that we're looking at as we're moving forward and talking about EGAN. And I know this chapter feels pretty dense as you start reading it. He starts to use a lot of equations and starts to use a lot of the terminology, assuming that you have a baseline understanding. So hopefully this piece will put everything in perspective and give you at least an understanding, and it makes more sense as you read through it a first time, a second time, a third time, and maybe more. So let's first look at this graphic here, and this graphic representation can really represent the full airways. However, it's really giving just looking at how we might look at the structures if we looked at it from an airways perspective, the upper airway to conducting airways, and then down to the lung itself and the alveoli and the periphery. So that's how we're going to look at it. And so first off, I just want to take a look at this and think about, well, what are each of these symbols? And so let's take a look at that. So PaO is, again, that big P. We see it here, we see it over here, we see it here, we see it here, we see it here. We see it, of course, all the way here. And of course, we see it over on the left-hand side. We see them here. And again, we've looked at pressures, and we're looking at the partial pressure. And in this case, we're looking at the pressure of certain areas. And if we look at the AO and we come up here, we see it's the pressure at the airway opening. And so looking at this graphic, we see it's really the entry point. We see here airway opening pressure. We see it in the trachea. However, I would move it anywhere to the upper airway to just before we get to the carina. Okay, and so we could call that the airway opening. We could even call it just outside of the body when we're looking at that here. Okay. Now, as we move into the lung, I want to go down the conducting airways. We come through the airway opening down to the airways, and we get to the lungs themselves. And we know that the lungs are mostly comprised of alveolar tissue. Okay, and so this is comprising the alveolus, and we can see then here in the next piece, we see the pressure at the alveolar level or the alveolus, and that's denoted by a big A. And that's important to remember and distinguish that when we look at a big A, and of course it's subscript, but it's still a capital A, we're looking at, and if we come here, we're looking at alveolar pressure. Subscript big A, P, alveolar pressure. Okay. Now, as we move through the alveolus, to the chest wall, which would be here on the outside. Remember, we know that we have that connection of the lung, the visceral pleura, the pleural space, the parietal pleura, and the chest wall. Okay? So now when we're looking at that connection, and we've said that that pleural space is really a potential space, but that's a very important space because when we're looking at the lungs and we're looking at gas movement, we're really looking at what are the relationships to pressures, okay? And so already we've looked at airway opening pressure, we've looked at alveolar pressure, and now within the pleura, actually, and remember, we've talked about there's coupling of those two, and there's actually a vacuum, so that tells us something about the pressure in there, and that's important to note. And we're going to talk at great length about that pressure in the pleural space, and we denote that by a PL subscript pressure, so that's pleural pressure. And so when we talk about pleural pressure, we're talking about what is that pressure defined in that pleural space, which again is a potential space. And so here we have pleural pressure. Here we have the denotation of pleural pressure. And again, you have your definitions, which the pressure is measured in the pleural space. And we'll talk about why would we want to know that? Now, as we move through from, again, the alveolar pressure to the pleural pressure, then we're coming out to, I'm going to hold off on this one here and go over here to the body surface pressure. And so when we're looking at the body surface pressure, BS subscript pressure, body surface pressure, it's of course measured at the body surface. And we've already been talking about this pressure. And really, the pressure that exerted on our bodies is really the ambient pressure that we've been talking about, the atmospheric pressure, which is the barometric pressure. Okay? And so when we're talking about body surface pressure, we're talking about just ambient pressure overall. All right. So again, we have the different pressures that are denotated on this side, and then there's the pressure of the musculature, okay, or the muscles of ventilation, and looking at that change in muscular pressure. And we've talked a little bit about that. Of course, that's the force we're looking at in normal resting breathing. We're looking at the diaphragm and the intercostals. Those really are the starting point at what happens when we're breathing in and out, because they exert the energy, they exert the change in pressure from that effort of energy that we see from the musculature. Okay, so now on this side here, on the right side, we're seeing the scientific symbol that's really denotating the airway opening pressure. We're looking at the lungs, which is really the denotation of the alveolar pressure. We're looking at the pleural space, which also contains a pressure. And then we're looking at body surface here, which is looking at the pressure that's exerted on the chest wall itself, okay? And so this here on this side really just is looking at all the different structures and then how we denote the various pressures within the respiratory system. Now, as we move over to this diagram on the left, I'm really going to be looking at both this diagram and this diagram as we start thinking about and start looking at what's happening during the respiratory cycle. And so again, you can see here, we have the airway opening pressure, and that's denoted by the upper airway to the trachea. But remember, also airway opening pressure could be right here, just as I'm taking a breath in my upper airway. We're denoting alveolar pressure by the alveoli, and we know that there are hundreds of millions of alveoli. And again, this graphic here is really just looking at one of those. but in actuality, there are millions, hundreds of millions of those. Okay? And then our pleural pressure, again, is looking within the pleural space, and then body surface pressure is what's being exerted on the chest wall and the body itself. Okay? So as you do your reading, I'd have you read Egan, and when Egan says one of these, then come back to these graphics and try to look at what Egan might be talking about. Now, as we look at breathing, and this graphic here gives us a graphic of looking at inspiration, and that's this graphic on the left, and expiration, this is the graphic on the right. Now, in order to think about, well, as we're looking at pressures, what is our baseline? And so in our previous module, when we were looking at and reviewing anatomy of the respiratory system, we did introduce the concept of barometric pressure at sea level, and we said that standard is 760 millimeters of mercury. Okay? And that is always true. We are always seeing this barometric pressure being exerted. As you noted, talked a little bit about in your reading, but as you also noted on the test, I gave you an example where that barometric pressure would change. And one of the ways it changes is as we go higher in altitude, that barometric pressure, that pressure that's pushing downward, gets less. And such as we were looking at Denver, Colorado, that pressure decreased slightly to 750 millimeters of mercury. However, for us and our intents and purposes, 760 millimeters of mercury is staying the standard. Now, what I also want you to note is now we're starting to talk about pressure, and we're starting to talk about breathing patterns. Notice that our pressure units, let's go ahead and get this here. Our pressure unit is going to change from millimeters of mercury to centimeters of water pressure. cm, centimeters, H2O, water. And so when we're talking about airway pressures and when we're talking about breathing patterns, we're now going to change the standard to centimeters of water. Okay? Now note the equivalence here that when we're looking at barometric pressure, that barometric pressure at sea level is 760 millimeters of mercury. However, when we start looking at airway pressures, and we're now starting to look at centimeters of water, that baseline pressure, even though it's at 760 millimeters of mercury, we now set that standard to 0 centimeters of water. Okay? So you can think of this 760 millimeters of mercury barometric pressure as the same standard as airway opening pressure or baseline pressure when we're talking about respiratory mechanics of 0 centimeters of water. Okay, so I want you to think about that and now think about, so when we're talking about that pressure being exerted, while we know it's this here, 760 millimeters of mercury, we know that the baseline is going to be at 0 centimeters of water. Okay. Now I know that I focused in on that, but I hope it starts to become helpful because as we're now starting to look at these standards, now we want to look at, well, what happens during inspiration and what happens during expiration? And overall, this graphic on the left side talks about inspiration. And when we're talking about inspiration and we're talking about expiration, we're talking about what happens with gas movement. And we know that during inspiration, the inspiratory cycle of breathing, we know that air goes in, and we know on exhalation or expiration, air comes out. And what allows that to happen? Well, let's first talk about what happens to make a pressure gradient. And when we talk about pressure gradients, we're talking about two places. In general, we're going to get more specific because there are a lot of different places we'll look. But what we want to do now is we want to start looking at, give me a second here, I've got a new little tool that I'm playing with here. That when we're starting to talk about pressure gradients, we're wanting to talk about these in relationship. So as we're looking at this here, and as we're wanting to look here for the left-hand side, we're looking at pressure gradient between what is outside and what is inside the lung. So here I'm looking at airway opening pressure. We could be looking at that airway opening within the upper airway, but all of that is airway opening pressure compared to what is the pressure in the alveolus, okay? And so we can call that a pressure gradient over here, okay? That pressure gradient. And so when we're looking at that pressure gradient, gas will flow if we make a pressure gradient from a higher pressure to a lower pressure, okay? So now we have to start looking at those pressures. And so we're going to start here outside. And right now, when no gas is moving, such as I'm at end exhalation, I'm relaxing, that must mean that the pressure between what is outside and what is inside, what is the baseline atmospheric or ambient pressure compared to what the alveolar pressure is equal, okay? But what happens during inspiration? And so first off, when we're looking at inspiration, we know that the muscles contract. We've talked about that on inspiration. The diaphragm, the musculature contracts and pulls the diaphragm down, okay? And so we see that pull of the diaphragm. We see the pull of the diaphragm, and it's pulling downward. And the intercostals over here, they also, the musculature contracts, and it actually pulls the chest wall outward. So we have the chest wall being pulled up and outward. We have the diaphragm being pulled down. And what that does is that creates an increase in the intrathoracic cavity. Now, with that increase in intrathoracic cavity, you can think about that as making a vacuum in there because that space is now getting bigger and there's a void. So just to say during inspiration, we start to see a negative pressure or a pressure gradient that's more negative in the lung compared to the pressure that is more positive outside or the upper airway or the airway opening. And so when we see that pressure gradient of positive compared to negative, then we're going to see gas go from a more positive pressure down to a more negative pressure, and then we can see gas moving into the airway. All right, so first off, again, I'm going to go that during inspiration, we see again first the energy being exerted by the muscular activity, contraction, moving the diaphragm down, moving the intercostals and the chest wall out, causing the chest wall itself to become bigger and more negative. And that creates a pressure gradient between what's outside, which is now more positive, compared to the alveoli, which is more negative, and gas will move in. Okay. Now, how much gas moves in depends on what that pressure gradient is, and we're going to talk about that at a later point and practice that. Okay. Now, what causes gas to come out? Okay, and so again, on the right-hand side, we're seeing the graphic that shows expiration. And so when we're looking at, again, expiration, well, then what happens? Well, in inspiration, we see the diaphragm and the intercostals contract, active, energy is applied, and what happens during expiration? Well, what happens in expiration is the diaphragm and the intercostals are allowed to relax. So when they're allowed to relax, that pressure that energy that's been exerted is now allowed to relax. And when that happens, then we see the diaphragm relax back into its normal state, and it actually relaxes upward. We see the chest wall relax and actually push inward, okay? Push inward. And then because that happens, we see now that that pushing actually increases pressure. And you can see I'm making these plus signs, increases pressure. Compared to outside, and so what happens outside now is there is a pressure gradient that's more positive in the lung than what is in the upper airway and outside. And so then gas goes from a higher pressure to a lower pressure and moves out of the lung and into the ambient air, the airway, and then of course out. Okay, so note on inspiration, we see the pressure gradient more positive outside than inside the lung because the diaphragm and the intercostals, they contract, they make the chest bigger, they make the alveoli and the lungs more negative in pressure compared to outside, more positive, and gas moves inward. Now, during exhalation and expiration, we look at the diaphragm and the intercostals, they relax and they go back to their natural state, which means that the diaphragm goes up, the intercostals relax and allow the chest wall to go back to its natural state. And all of these push onto the lungs, making the pressure more positive in the lungs, the alveoli, compared to outside. And so then gas moves outward. Okay. Now you'll note the last piece that I haven't talked about is, well, what happens when pressures equalize? So as the gas either moves in or either moves out, what happens is gas moves until the pressure equalizes between outside and inside, between outside and inside. And so we say gas movement will cease, or there will be no gas movement once those pressures equalize. Okay, and we're going to put this to practice soon here when we meet and look at those pressures, because we haven't even talked about, well, what are all those pressures at any given time? And right now we're just looking at the relationship. Which pressure is higher at any given point? And during inspiration, pressure is higher outside than inside the lung, so gas will go from a higher pressure to a lower pressure into the lung. And during exhalation, pressure is greater inside the lung than outside the lung once the diaphragm and intercostals relax, and that will move gas from inside the lung to outside as we move forward. Now I want to look at this graphic, and this graphic, what it does show here is it takes a table 11.2, and I want to talk a little bit about this here, just to say that as we're looking at differences in pressure during any given point during inspiration and expiration, we want to look at the relationship of those pressures. Okay? And so table 11.2 names that relationship. So if we're looking at a relationship of two different pressure measurements, we call it something and we use a certain symbol, okay? So again, in the previous slide, we looked at this graphic and we looked at airway opening pressure. Oops. Get my laser pointer. Airway opening pressure, alveolar pressure here, airway opening pressure here, or out into ambient atmospheric area. Pleural pressure is measured in the pleural space, and then body surface pressure is measured outside of the chest wall. Okay? And so body surface pressure can also be equated to ambient pressure. Okay? And so now as we're looking at all of these, we can look at, well, what is the relationship between airway opening pressure and alveolar pressure? And so if we come down here and we look at the second entry, we can see that there is, under definition, a relationship between airway opening pressure and alveolar pressure, and we call that trans-airway pressure difference, or the trans-airway pressure. And we delineate that by a change in trans-airway, TAW, subscript pressure. Okay? And the relationship between alveolar and pleural pressure is called transalveolar pressure. So I transcribed it up here, but if we come down to the difference between alveolar and pleural pressure, we could see that it's called transalveolar pressure. And this triangle is the delta, the change in pressures via the transalveolar pressure. And then at least on the graphic, the difference between, or the relationship between the pleural and body surface pressure is called the trans-chest wall pressure. And we can see it here, the relationship between pleural and body surface pressure is called the trans-chest wall pressure. Now, one of the things that we can do is we can look at some others and look at the relationship between the airway opening pressure and the body surface pressure. And so if we look at that relationship and look on our table, we can see that the relationship between the airway opening pressure and the body surface pressure is called trans-respiratory pressure. And so that's the delta in trans-respiratory pressure. And if we wanted to look at the relationship between airway opening pressure and pleural pressure, we can again come through here and find the relationship between the airway opening pressure and the pleural pressure. We would call that transpulmonary pressure. And that would be the delta of the transpulmonary pressure. So I want to give you these pieces so that we could look at and start talking about the different relationships. So right now, remember in this module, we've talked about baseline, or at least airway opening pressure, is when we're now switching to centimeters of water. If you can remember, that would be, let's see if you can remember, that would be in normal resting phase, 0 centimeters of water. Okay. And that's the baseline pressure that we've started with, and we've not quantified the alveolar pressure or the pleural pressure, but we could also say right now, again, body surface pressure as we're normal function is the same as airway opening pressure, which again is 0 centimeters of water. Okay, so we can at least define airway opening pressure and body surface pressure really as the same, 0 centimeters of water, 0 centimeters of water. And again, what we know, again, if we were talking about barometric pressure, that would be equal to 760 millimeters of mercury. However, our baseline in respiratory pressures are at 0 centimeters of water. Now, before we finish here, I just want to now look at the the graphic one more time, and now start to look at some waveforms. Okay, and we're going to be practicing this at our next session, but we're going to start looking at how would we take variables and how would we be able to look at them in a graph? Because ultimately, as you start applying ventilation, and especially in the intensive care unit with ventilators, we start looking at all of these graphics. So while I haven't explained any of this, we'll be talking about that in our next session. But for now, I just wanted to give you this graphic so you can see that. Okay. So I hope this was helpful. I know that there's a lot of new terminology, and I would encourage you to start, looking at these here, print these out, and as you're reading Egan, to go back and identify when he says alveolar pressure, to look at it here on the graphic, so that you get an idea as he starts stating things like, let's talk about transrespiratory pressure, transpleural pressure, or transalveolar pressure. What are we talking about? Okay. Thank you.